I want to start with a confession. Almost every week I see a headline saying a quantum computer just did something impossible. It cracked a code. It tried every possible answer in the universe all at once. And every week a small voice in my head says, wait, is any of that actually true? Because in my quantum class, the machine we're describing is fragile and strange, and it does not sound remotely like the superhero in the headlines. So today, I don't want the sales pitch. I want the honest version. What can these things really do, and what is pure hype?
That is exactly the right instinct, and I love that you LED with it. You're describing the single most oversold topic in all of physics. There is more nonsense written about quantum computing than about almost anything else in science. And the sad part is, the real story doesn't need the hype. The truth is astonishing, just in a completely different way than the headlines claim. So my goal today isn't to deflate your wonder, it's to hand you a truthful picture, so that every time you read, "Quantum computer solves the impossible," you'll know what to believe and what to laugh at.
Okay, I'm ready to have my illusions carefully removed.
Gently. And here's the promise I'll make. I'll be relentless about one distinction all episode. There are things that are proved and solid, textbook physics. There are things that have been demonstrated, but only on contrived, useless by design tasks. And there are things that are merely hoped for. 3 buckets. Almost all the confusion in the world comes from someone quietly moving a claim from the 3rd bucket into the 1st. So I'll keep telling you which bucket we're in.
Deal? Where do we start?
Somewhere reassuring, with something you already know cold. A qubit is a thing you have already met. Tell me, in your first quantum course, what was the simplest system you studied? Not the hydrogen atom, simpler. The absolute minimum.
Honestly, a 2-level system, a spin 1/2 in a magnetic field. It can be up, it can be down, or it can be in a superposition of up and down. We did it to death. And the double slit, of course, where a single particle somehow goes through both slits at once.
That's it. That's the whole foundation. A quantum bit, a qubit, is nothing more exotic than that. Take any 2-level quantum system. A spin that can point up or down. A photon polarized horizontally or vertically. An atom sitting in its ground state or one energy level up. Call one of those states 0 and the other 1. And now, because it's quantum, it can be in a superposition of both. We write it as some amount of 0 plus some amount of 1.
So when people say qubit, I should just mentally translate it to the spin 1/2 we already did.
Literally. There is no new physics in the word qubit. It's the 2-state system you already understand, given a job. The 2 numbers out front, the amount of 0 and the amount of 1, are the amplitudes. They're complex, and their squared sizes have to add up to 1, because the thing has to be found somewhere when you look. You've seen that constraint too.
I have. Okay, here's where my hype detector already starts twitching. People love the coin picture. They say a qubit is like a spinning coin, both heads and tails until it lands. Good picture or a trap?
It's a good picture, with a sharp limit that you have to say out loud, or it quietly lies to you. Use the coin to feel the in-betweenness. It's genuinely not decided yet. Fine so far. Here's the limit. A spinning coin, deep down, is actually either heads or tails at every instant. You just don't happen to know which. That's ignorance. A qubit is not ignorance. It is genuinely both at once, and the 2 amplitudes are complex numbers that can do a thing probabilities can never do.
Which is?
They can cancel. 2 amplitudes can meet crest to trough and wipe each other out to nothing. A probability can't do that. Probabilities only ever add up. The moment you let coin quietly become, we just don't know which, you've thrown away the entire reason quantum computing exists. So keep the coin, but tattoo the limit onto it. Both at once, and they can interfere. Hold on to that word. Interference. It's the hero of the whole story.
Noted. Amplitudes can cancel, probabilities can't. That already feels like the crack where all the real weirdness gets in.
It's the whole ball game. Now let's build the machine, the exponentially large hidden state. One qubit carries two amplitudes, the amount of 0 and the amount of 1. Now put two qubits together. How many amplitudes?
2 qubits, so the states are 0, 0, 0, 1, 1, 0, 1, 1. 4 combinations, so 4 amplitudes.
3 qubits.
8. It's doubling. Every qubit I add doubles the number of amplitudes.
And that doubling is the single most important fact in this field. With n qubits, the state is a list of 2 to the n complex amplitudes. Not n amplitudes, 2 raised to the power n. It explodes. 10 qubits, about 1,000. 20, about 1,000,000. 50, past a quadrillion. And by the time you reach 300 qubits, the number of amplitudes describing that one machine is larger than the number of atoms in the entire observable universe.
Wait, 300 qubits, 300 little spins. And to write down its state on paper, I'd need more numbers than there are atoms in the cosmos.
More numbers than atoms in the cosmos. And to be clear, this is completely solid, bucket 1, proved textbook physics. That vastness is real. It is not a metaphor. The state of n qubits genuinely lives in a space of 2 to the n dimensions. This is exactly why simulating quantum systems on an ordinary computer is so brutally, hopelessly hard. Nature tracks those numbers effortlessly. Your laptop falls over instantly.
Okay, so this is where every hype article lives, right? This is the sentence. A quantum computer holds exponentially many numbers, so it can try every possible answer simultaneously. I have read that literally 100 times. Everyone says it. Tell me it's true.
I'm so glad you said it in exactly those words, because that sentence is the great lie of quantum computing, and I get to spend the next 10 minutes taking it apart with you. It is the single most common thing people believe, and it is wrong. Not exaggerated, wrong. The state is real. The conclusion people draw from it is false. And the gap between those two things is the whole subject. So let me show you the trapdoor that everyone falls through. The measurement trap. Here's the question that breaks the myth. You've got your n qubits sitting in this gorgeous superposition of 2 to the n possibilities. All the answers are in there somewhere. Now, how do you get an answer out?
I measure it. I look.
You measure it. And what does your first-year quantum course tell you happens when you measure?
Oh no. Oh, I see where this is going. When I measure, I don't get the whole wave function. I get one outcome. The state collapses. I just get one result.
Say exactly what you get. You measure n qubits. You get back n classical bits. One string of zeros and ones. That's it. Not the 2 to the n amplitudes. Just n bits. One string. Chosen randomly, with the probability of each string set by the size of its amplitude squared. And the instant you look, the whole glorious superposition collapses to that one string and is gone. You cannot go back and read the rest.
So the machine really is holding all 2 to the n amplitudes in there. But when I reach in to read them, I'm only allowed to pull out one string at random, and the act of pulling it out destroys everything else.
That is the entire crux of this episode, and you just said it perfectly. The amplitudes are real, and the amplitudes are unreadable. Both. At the same time. There's a vast, hidden ledger inside the machine, and measurement lets you glimpse exactly one entry, chosen by a roll of the dice, and then it burns the ledger.
That's almost cruel.
It's the cruelest and most important fact in the field. So now watch what happens to the hype sentence. The machine tries every answer at once. True-ish, the state does contain them all. and reads off the winner. Flatly, provably false. You do not get to read off the winner. You get one random string. If you just threw all your possibilities into a superposition, gave them roughly equal amplitudes, and measured, you would get a uniformly random answer. A coin flip across all possibilities. No better than closing your eyes and guessing.
So the exponential state, all by itself, buys you nothing?
All by itself, nothing you can use. Zero. I want that to land hard because it's the opposite of what everyone tells you. Raw superposition is not a super-fast parallel search. Raw superposition plus measurement is a very expensive random number generator. The exponential vastness is real, and it is, on its own, useless. There has to be a second ingredient. And that second ingredient is where the genius lives. Killing the myth by name. Let me name the false picture out loud so you'll recognize it forever in the wild. People say a quantum computer is like exploring a maze by sending a copy of yourself down every corridor at once, and then the lucky copy that finds the exit reports back. Parallel universes doing your homework. It's a lovely image. It is completely wrong, and here's the exact reason.
Because the copies can't report back.
Because the copies can't report back. Measurement hands you one corridor, picked at random, and it's overwhelmingly likely to be a dead end, because dead ends vastly outnumber exits. The many copies picture never explains how the machine steers the random draw toward the right answer. And without that steering, a trillion universes computing for you gets you precisely one random useless string. So when you hear tries all paths in parallel, mentally finish the sentence with, and then hands me a random one and deletes the rest. Suddenly, it doesn't sound so magic, does it?
No, it sounds like I paid for 1 billion lottery tickets, and I'm only allowed to look at one of them, and it's almost certainly a loser.
That is a genuinely excellent way to put it. So the real question is this. Can you rig the lottery so the one ticket you're allowed to look at is overwhelmingly likely to be the winner? And the astonishing answer is, sometimes yes. Not by parallelism, by interference. What actually does the work? Back to the double slit. Why is it the most important experiment you ever did?
Because a single particle goes through both slits and the two paths interfere, where the waves arrive in step, crest on crest, you get a bright fringe. Where they arrive out of step, crest on trough, they cancel and you get a dark fringe, a band of nothing, even though particles were pouring in.
Hold on to that dark fringe because it is the secret of quantum computing. A dark fringe is a place where amplitude was sent from both slits and it cancelled to nothing. Particles could have landed there and instead zero. Now, a quantum algorithm is a machine for manufacturing dark fringes on purpose.
Manufacturing dark fringes, say more.
Think of every possible answer to your problem as a spot on the screen. The wrong answers and the right answer. A quantum algorithm is a carefully choreographed sequence of operations, and its entire job is to route amplitude so that every wrong answer sits in a dark fringe. Multiple paths lead to each wrong answer, and the algorithm arranges for those paths to arrive out of step and cancel. Crest meets trough. The wrong answers wipe themselves out. Meanwhile, the paths leading to the right answer are arranged to arrive in step, crest on crest, and pile up. That answer gets a bright fringe. Its amplitude swells.
And then when I finally measure.
When you finally measure, remember the rule. You draw one string, with probability set by amplitude squared. But now the wrong answers have almost no amplitude. They cancelled, and the right answer has almost all of it. The random draw is rigged. Overwhelmingly, the string that comes out is the right one. You looked at your one lottery ticket, but the algorithm quietly made almost all the other tickets vanish before the draw.
Okay, that's beautiful, and it's completely different from what I thought. The power isn't that it checks everything in parallel. The power is that it makes the wrong answers destroy each other.
Engineered cancellation. That is the honest, three-word summary of what a quantum computer does, and you will almost never see it in a headline. It's not parallelism, it's interference, choreographed so precisely that wrongness cancels and rightness survives. Now, notice I keep using the words carefully and choreographed. There's a catch buried in there, and it's the catch that keeps everyone honest.
There's always a catch.
You can only set up that cancellation if the problem has a special hidden structure for you to exploit. A periodicity, a symmetry, some deep regularity in the mathematics that lets you design the interference pattern. And here is the honest, slightly deflating truth. Most problems don't have that structure. For most problems, there is no clever pattern of cancellation to build, and so there is no quantum speed-up at all. None. Not a faster computer, a different one.
So this kills another thing everyone says. A quantum computer is basically a super-fast supercomputer. That's wrong too, isn't it?
It's wrong, and it's the second myth I want you to swat down on sight. A quantum computer is not a faster computer across the board. It won't load your web pages or play your video any faster. For the overwhelming majority of tasks, it offers no advantage whatsoever, and for many, it's provably no better than your laptop. What it is a differently abled machine, spectacularly good at a narrow, special class of problems, the ones with the right hidden structure, and utterly ordinary at everything else.
So the right slogan is different tool, not faster tool.
Always. Think of a sailboat. It isn't a faster car, it's useless on a road, but on water in the right wind, it does something no car can. A quantum computer is a sailboat. The question is never whether it beats your laptop in general, only whether your specific problem is water or road.
What are the water problems? The ones with the structure?
I'll name two, and then deliberately not explain them, because they'd swallow the whole episode. There's a famous one, Shor's algorithm, that exploits a hidden periodicity in arithmetic and could, in principle, factor enormous numbers, which is exactly what today's internet encryption relies on being impossible. And another, Grover's algorithm, that gives a more modest speed-up for searching. Both are real, both proved on paper, and both require a big, reliable, error-corrected machine that nobody has built. Name them, know they exist, move on. The list of problems where quantum genuinely wins is short and special, not everything but faster.
And the most honest thing I can carry around is exponential state, yes, real. Speed up from parallelism, no. Speed up from engineered interference, yes, but only on special problems.
If you remember nothing else, remember that sentence. You are now better calibrated than most of the people writing the headlines. But we've been talking as if these machines run perfectly. They don't. And why they don't is the next chapter of the honest story. Why it is so brutally hard to build. Everything I've described depends on the superposition surviving, untouched, while you perform your careful choreography. And superpositions are the most delicate things in the physical world. Any stray interaction with the outside world, a wandering photon, a whisper of heat, a magnetic hiccup, acts like an accidental measurement. And what does a measurement do?
It collapses the state. So the environment is constantly, accidentally, measuring the machine and wrecking it.
Constantly. That leakage of quantumness into the environment has a name, decoherence, and it is the enemy. Your beautiful interference pattern washes out in a tiny fraction of a second. So people ask the obvious question, can't we just make backup copies? Store the information redundantly, the way we protect a file by saving 3 copies, so if one gets corrupted, we outvote it.
That seems reasonable. Why not just copy the qubit a bunch of times?
Because of one of the deepest theorems in quantum mechanics, and it's beautiful. You cannot copy an unknown quantum state. at all. It's called the no cloning theorem, and it's not an engineering limitation, it's a law. So the whole classical strategy of just make backups is off the table from the start.
So how do you protect information you're not even allowed to copy, and that you can't look at because looking collapses it?
Now you're asking the exact question that stumped people for years, and the answer is genuinely one of the cleverest ideas in modern physics. It's called quantum error correction. You don't copy the qubit, you spread its information out, smeared across many physical qubits, woven together in an entangled web. No single one of them holds the answer. The answer lives in the pattern among them.
But you still can't look at them to check for errors. Looking collapses everything.
And here's the trick, the truly gorgeous part. You never measure the data, you only measure relationships. You ask questions like, do these two neighbors still agree with each other? That question has an answer, yes or no, that tells you whether an error crept in, without ever revealing or collapsing the actual value being stored. You're checking whether the web is still intact, not what it says. And from a whole pattern of those "do the neighbors agree" answers, a classical computer can figure out where an error happened and how to reverse it, all without ever peeking at the protected information itself.
So error correction is like backup copies.
Use the backup analogy for the motivation, redundancy, protecting fragile information by spreading it out. But immediately flag the limit loudly. It is not copies. Copying is forbidden. It's a single piece of information smeared across an entangled web, protected by measuring only the relationships, never the data. And the price of all this cleverness is steep. It takes many shaky physical qubits, all working together, to protect the information of just one good steady qubit. We call that one protected qubit a logical qubit. Many noisy physical qubits woven into one reliable logical qubit. Remember that phrase, physical versus logical, because it's where a lot of headlines cheat you.
Okay, so now I understand the dream, and I understand why it's hard. Where are we actually, right now? What's real?
Now we get to the frontier, and now I get to keep my 3 buckets very, very close at hand. The Frontier, Part 1, The Claim That Unraveled. Let's start with the moment quantum computing exploded into the headlines. The year 2019. Google, with a superconducting chip they named Sycamore. 54 tiny superconducting circuits, each one a qubit, though one was dead, so 53 working. And they ran a task, and they published it in Nature, and they used a word that had been coined years earlier, in 2012, by the physicist John Preskill. The word was supremacy. Quantum supremacy.
I remember this. This was everywhere. What did it actually do?
This is where honesty matters most, so let me be precise. The task was something called random circuit sampling, and understanding it is the key to not being fooled. They set up a deep, tangled, essentially random quantum circuit, ran it and measured. Because of interference, some output strings are more likely than others, in a pattern that's fiendishly hard to predict. The task is just produce strings with that hard-to-predict distribution. Google's chip did it in about 200 seconds, roughly 3 minutes, and they estimated the world's best supercomputer at the time, a machine called Summit, would need something like 10,000 years to reproduce the same output.
10,000 years versus 3 minutes. That's the number that was on every front page.
That's the number. Now let me tell you everything the front pages left out, because it's a perfect case study in reading these claims. First, honesty about the machine, and to Google's great credit, this is right there in their own paper. The fidelity was about 0.2%. Roughly 99.8% of the runs were essentially noise. The real quantum signal was a faint needle in a haystack of garbage. A statistically solid needle, it stood out at about 5 standard deviations, so it was really there. But a whisper, not a roar.
So it worked, but barely, and mostly it was noise.
Mostly noise, with a real signal poking through. Second, and this is the big one, the task solves no practical problem. None. Nobody on Earth needs the output of a random circuit. It was chosen precisely because it's useless, because a structureless task is the hardest thing for a classical computer to fake. A benchmark designed to be hard, not a problem anyone wanted solved. That's bucket 2. Demonstrated but contrived.
And third, you've got that look.
Third, the 10,000-year gap did not survive. Within days, a rival team at IBM argued a smarter classical method, using clever disk storage, could do the ideal task in about 2.5 days, not 10,000 years. And then it got worse for the claim. Over the next couple of years, groups in China reproduced Sycamore's task on ordinary classical computers, on clusters of graphics chips, at higher fidelity than the original, and argued it could be done in hours, some later work in minutes or seconds.
Hold on, so the 10,000-year gap
Is gone. Evaporated, within a few years, as classical algorithms caught up. And I want to be scrupulously fair. This does not mean Sycamore was fake. It really did run a deep, genuinely entangled 53-qubit computation. That's real, bucket 1. But the story the public got, quantum has crushed classical computing forever, was wrong the moment it was printed, and the science itself proved it wrong. This is the pattern I need you to memorize. Impressive quantum demonstration, breathless headline, and then, quietly, months or years later, a classical algorithm catches up, and nobody writes that headline.
That is genuinely not how I remembered this story at all.
Almost no one remembers the second half. The retraction never trends. Which is exactly why this episode exists. The Frontier, Part 2, the honest name for now. So what era are we actually in? Preskill, the same physicist who coined supremacy, gave it an honest name back in 2018. He called it NISQ, Noisy Intermediate Scale Quantum. Read that slowly. Noisy, the qubits are error-prone, and there's no full error correction yet. Intermediate scale, we're talking roughly 50 to a few hundred qubits, big enough to be interesting, nowhere near big enough to change the world. His own line, and I love it for its honesty, was that a machine with about 100 qubits will not change the world right away.
The guy who named quantum supremacy also went out of his way to say, and by the way, don't expect miracles.
The honesty was baked in from the start by the serious people. It's the marketing that ran off without them. So where does the current scale sit, in the middle of this decade? The honest headline is, somewhere between roughly 100 and a few thousand physical qubits, depending on whose machine and how you count, and every one of them is still too noisy to run a big, useful algorithm end to end.
Give me the details. And I especially want you to tell me about the ones with thousands of qubits, because that sounds like it should be a huge deal.
Good, because that's a trap, and I'll spring it on you in a second. 3 families of hardware, briefly. First, superconducting circuits, the Google and IBM approach. Tiny loops of superconductor kept colder than deep space. IBM's chips run in the range of about 120 to 150 qubits, with names like Eagle at 127 and Heron at 156. Second family, trapped ions, individual charged atoms held in electromagnetic fields, the quantinuum and ion Q approach. Fewer qubits, one flagship has about 56, but the cleanest operations and the best connectivity. Every qubit can talk to every other. Fewer but better behaved.
And the third? The thousands one?
The third is neutral atoms, whole atoms held in place by focused laser light, the approach of groups like Cura, atom computing, and university labs. And here's the eye-popping number, and here's the trap. In the autumn of 2025, a team at Caltech announced they had trapped roughly 6,100 cesium atoms in a single array. and one company runs an array with more than 1,000 atomic sites. 6,000. That sounds like it dwarfs everything.
It does. 6,000 versus 150? That sounds like they lapped everyone.
And this is a big myth. Trapping 6,000 atoms is a genuine, beautiful milestone, but it is not a 6,000 qubit computer running algorithms. It's an array, 6,000 atoms held beautifully still in a grid. Holding atoms in place is one thing, making them interact in controlled ways, running gates between them with high accuracy, weaving them into error correction, running an actual algorithm, that is a completely different and far harder thing. The number of atoms you can trap is not the number of qubits you can compute with. Raw count is not computing power.
So when a press release leads with a giant qubit number,
Your alarm should go off. Ask, are these qubits actually computing or just being held in place? A machine with 50 superb, well-connected, error-corrected qubits would crush a machine with 10,000 noisy, disconnected ones. Big numbers make big headlines. They do not make big computers. The count is the easiest thing to inflate and the least meaningful to brag about. The Frontier, Part 3. Willow and the Two Stories. Now I want to tell you about the single most important, genuine result in recent years. It's real, it's peer-reviewed, and it's exactly the kind of quiet, hard-won progress that never gets the headline it deserves. And in a perfect twist, the very same chip also produced a loud, hype-driven claim that got all the attention, and that you should mostly ignore. Same chip, two stories. Learn to tell them apart, and you've learned the whole skill.
same chip, two stories. Okay, what's the chip?
Google, again, late 2024, a chip called Willow, about 105 physical qubits. Story 1, the real one, is about error correction. Remember, the whole dream of a useful machine depends on turning many noisy physical qubits into one steady logical qubit. And for about 30 years, there had been a terrifying open question. When you scale up the error correction, when you use more physical qubits to protect your one logical qubit, does the error rate actually go down? Or do the new qubits bring in so many new errors that you go backwards?
Right, because every physical qubit you add is another thing that can break. You could be adding more problems than you fix.
Exactly the fear. And what Willow showed, and this is bucket 1, solid, peer-reviewed in Nature, is that they crossed the line. They built their error-correcting code at 3 successive sizes, and each time they made the code bigger, the logical error rate went down. Each step up cut the error by roughly a factor of 2, and the protected logical qubit finally outlived its own best physical qubit, lasted more than twice as long, with a classical computer decoding the errors in real time as it ran. Physicists have a phrase for crossing that line: below threshold. It's the precondition for everything. It's the proof that scaling up helps rather than hurts.
That does sound like a genuine milestone. So why do you look worried?
Because of everything it is not, and here honesty earns its keep. Willow protected one logical qubit. One. And that logical qubit mostly just sat there and remembered. It stored information faithfully, which is exactly what you'd test first, but storing is not the same as computing. It did not run Shor's algorithm. It did not break encryption. It did not solve any problem. It demonstrated that the memory of a single protected qubit can be made to improve as you scale, in real time. That's a huge deal for the roadmap, and very far from a working quantum computer.
How far? Give me the honest gap.
A genuinely useful, fault-tolerant machine needs not one logical qubit, but thousands. And since each logical qubit costs you many, many physical ones, thousands of logical qubits means on the order of 1 million physical qubits, all below threshold, all at once. Willow has about 100 physical qubits and one logical qubit that remembers. The destination is around 1 million physical qubits and thousands of logical qubits that compute. Below threshold is the on-ramp, emphatically not the destination. So when someone tells you Google solved error correction, the honest correction is, Google showed, for the first time and beautifully, that error correction can get better as you scale, for one qubit that remembers. It's still an amazing sentence. It just isn't the headline one.
You said 2 stories, same chip. What's the loud one?
The loud one. The same Willow chip also ran a random circuit sampling task, the same useless benchmark family as 2019, and the announcement said it did in about 5 minutes what would take a classical supercomputer 10 septillion years. 10 septillion, that's a 1 followed by 25 zeros. A number so large it beats the age of the universe into insignificance.
10 septillion years. Okay, that is exactly the kind of number that ends up on a magazine cover.
And it did. And here's what you need to know, and it's simple. That number is from a company blog and announcement. It is not in the peer-reviewed error correction paper. Those are 2 different things wearing the same chip's name. The septillion years number is attached to a random sampling task that is useless by design. Exactly the kind of contrived benchmark whose classical difficulty has a habit of collapsing later, just like 2019, so keep them in separate boxes. The error correction result, real, peer-reviewed, durable and modest, one logical qubit that remembers. The septillion years boast, loud, blog-level, contrived, and destined for the same scrutiny that shrank the last one. When you read about Willow, the durable thing worth caring about is the boring-sounding one.
The unglamorous result is the real one, and the glamorous number is the shaky one. That is almost a law at this point.
It is nearly a law of the whole field. And I'll add, so you have the honest state of play, that error correction is starting to scale beyond single qubits. Teams have demonstrated a few dozen logical qubits at once and run small algorithms on them across 2023 through 2025. Still small, still fragile, still mostly memory and simple circuits. The direction is genuine, the distance remaining is enormous, both true at once. The honest horizon.
All right, let me try to say the honest bottom line, and you tell me if I've got it. As of right now, has any quantum computer solved a single, useful, real-world problem faster than a classical computer? In a way that actually held up?
No, full stop. And I'll say it as plainly as I can because it's the most important sentence in the episode. As of the middle of this decade, there is no verified, useful quantum advantage on a practical problem. Not one. Every beyond classical milestone so far is either a contrived benchmark, random sampling, useless by design, or a physics demonstration. And a striking number have been matched or beaten by classical computers soon after. Sycamore's 10,000 years collapsed to hours. Another celebrated result a couple of years ago, a demonstration of so-called quantum utility, was reproduced and beaten by ordinary classical methods on ordinary hardware within months.
Within months, it's the same pattern again.
It is. And that pattern isn't a scandal, it's what real early science looks like. The scandal is only in pretending otherwise. Now let me be equally fair in the other direction, because anti-hype should never curdle into cynicism. There are newer results genuinely more honest than the old ones. In late 2025, Google reported a benchmark they called quantum echoes, run on a subset of the Willow chip, about 65 qubits. And the genuinely better thing about it is that it's repeatable and cross-checkable. Unlike the one-off random string from 2019, another lab could, in principle, run it and confirm it. They reported it running something like 13,000 times faster than the best classical method they knew.
So is that it? Is that the useful advantage finally arriving?
No, and this is a subtle, important distinction. It's the most honest advantage claim yet, and it is still not a useful problem solved. It's a physics measurement, a benchmark, verifiable rather than a random string, which is real progress, but it's still not a delivered application. Nobody's drug got designed, nobody's material got discovered, and its classical hardness margin will face the same scrutiny every previous claim faced, and might well shrink the same way. The honest label, promising candidate, still not usefulness. Not quantum has arrived.
What about the one everyone's actually scared of? Breaking encryption. Every few months I see quantum computers will break all encryption soon. How scared should I be?
Let me give you the real numbers, because they're clarifying. The best recent estimate from a Google researcher, Craig Gidney, in 2025 is that breaking the standard 2048-bit encryption that guards the internet would take under 1 million noisy qubits, running less than a week. And that's genuinely impressive work, because his own earlier estimate had been around 20 million qubits. The requirement dropped about 20-fold as the methods got cleverer.
Under 1 million. But you told me the biggest machines today have around 100 to a few thousand qubits, mostly noisy.
And you just did the honest arithmetic yourself. Under 1 million qubits is still roughly 1,000 times bigger than today's best chips, and it has to be a fault-tolerant, error-corrected machine, which nobody has at any real scale. So this improved, scary-sounding number is not evidence that anyone can break encryption soon. It's a measure of how enormous the gap still is. What it honestly is a reason to start migrating the world's cryptography to quantum-resistant methods now, because that migration takes many years and you want to be safe long before any such machine could exist. Prepare now because it's prudent, not because it's imminent. Different sentences and the headlines constantly merge them.
What about all the roadmaps? Companies keep announcing that by such and such a year, they'll have a fault-tolerant machine, or 100,000 qubits.
And every one of those dates is a target, not a promise. When a company says it aims for a large, fault-tolerant machine with a couple hundred logical qubits by the end of this decade and 100,000 physical qubits a few years after that, those are plans, ambitions. The honest verbs are aims for, targets, hopes to, never will. Roadmaps in this field have slipped before and will slip again, and that's normal for hard engineering at the edge of physics. Treat every future date as a hope with a logo on it, not a fact.
So where does that leave us? What's the actual open question, the one that a student like me could someday help answer?
Here's the honest horizon, and it's a double uncertainty. Two open questions stacked on top of each other, and I find that genuinely thrilling rather than deflating. Question 1. Is there a truly useful problem? A molecule for a new medicine, a material for a better battery, that happens to have the special hidden structure a quantum computer can exploit? We suspect yes, especially for simulating quantum matter itself, that's the most natural fit. But it is not proven for any specific valuable problem. That's an open question sitting in the hoped bucket. And question 2, running underneath it. Even if such a problem exists, can we actually build a machine reliable enough, big enough, error-corrected enough to run the algorithm before decoherence eats it alive?
And both of those are genuinely open. Nobody knows.
Both genuinely open. Nobody knows. And notice what that means. The entire justification for this enormous global effort rests on two unproven bets, and the honest people in the field will tell you so to your face. Which to me is far more exciting than the fake certainty of the headlines. Because it means the story isn't written. The person who finds the useful problem with the right structure, or who invents the trick that makes 1 million qubits behave, hasn't shown up yet. It might be someone in a quantum class right now, staring at a spin 1/2 and a double slit, thinking, wait, I understand every ingredient in this, so why can't I see how to make it win?
That's a much better feeling than the miracle machine is almost here.
It's the true feeling, and the true feeling is better. Hold on to the shape of it. The exponential state is real but unreadable. The power is engineered interference, not trying every answer at once, and only for special structured problems. The machines are real, small, and noisy. Error correction has crossed a beautiful threshold for one qubit that remembers, with a very long way to go. And nobody has yet beaten a classical computer on a useful problem in a way that survived scrutiny. And none of that honesty makes it less amazing. A machine that computes with the interference of possibility itself, built out of the exact strangeness you met in your first quantum class, with the biggest questions still wide open. You don't need the hype. The truth is the wonder. You just have to be brave enough to tell them apart.
The truth is the wonder. I think that's the whole series in 4 words.
Then we can stop there.